Alright, hello everybody. Now what I want to do is I want to just go over this classical PDEs as well as a boundary value problem, and then I will go in depth with each of these equations that you're seeing here on the screen. Okay, I'll first start with this, go real in depth, same, alright? But let's get an overall what is going on over here. So the very first one is called K, is the thermal diffusivity, and it is larger than 0. And I have over here U is actual temperature in this particular case. Okay, so I'm looking at the temperature distribution in a rod. Okay, that's a typical example of this 1D heat equation, and it is actually looking at it. The independent variables are x and t, so it's a time dependent. Okay, let's look at the second equation. The second equation is this A is actually the wave speed, and this is you can look well similar, right? But the right hand side is second order with respect to time, right? This is like if I have a string vibration, like guitar string, so I can obtain the vibration of that through this equation. Okay, it's still a function of time, right? Just want to highlight. And let's look at the last one. The last one is 2D Laplace equation. This is a very common equation as well. And the application wise, you can think of this as, let's say that I have like a rectangular plate over here, a thin plate, and I'm interested in the temperature distribution over here. However, there's no T here, time. So I'm only looking at steady state temperature distribution for this particular case. Okay. So as I mentioned, this heat and wave equation are time dependent, but there's only one dimension. That's the advantage of it, right? I don't see any y here. And Laplace is time independent, which means it's steady, but I have two dimensions that I need to consider. Okay. Actually, one thing, this is additional information, but Laplace's equation is extremely common. Actually, we have a mathematical operator for that. If you remember this, we use this in fluid mechanics as well, undergraduates too. So I have this second del square, whatever the parameter is, and the last one is del square this divided by del z squared. I can give example from fluid mechanics, and this will be velocity potential. I mentioned that up there when I was talking about the subsonic, hypersonic, supersonic. So it's the same thing. The velocity potential, if you look at it, this is the conservation of mass expressed in terms of the velocity potential function. Okay, but also something interesting to note. I want to actually go up here if I can squeeze myself in there. Let's look at these three equations from different angle. Do you remember that I called the parameter in front of this particular term as A in the previous segment, and in this particular case A is K, B is 0, C is 0. So I'm trying to calculate this B squared minus 4AC. If you don't know what I'm talking about, please visit the previous segment. I discussed this in more detail. Okay, but in this particular case, what happens is, well, B is 0, so that's this term is gone. A times C, C is 0, so I got myself 0. Okay, so what I get is here is my heat equation turns out to be a parabolic. Okay, it's a parabolic. Let's look at the wave equation. This time on, my A is equal to A squared, my B is equal to still 0, and my C is equal to, I'm not going to say 1, but minus 1. The reason is, the way that I write this was, this is supposed to be on that side of the equation, and the right hand side was equal to G of x comma y, right? So from here you can see my B squared minus 4AC happens to be positive, right? Because this A squared is positive, the C is negative, negative because it's positive, so I got myself a positive. So then this is referred to as hyperbolic. And last but not least, let's look at this. A is equal to 1 now, B is equal to 0, and C is equal to 1. And if I do B squared minus 4AC, A is positive, C is positive, so I got myself a negative value over here. So then this means that this is elliptical. So you can see that with these three in-depth studies that I will do, you will be able to approach a parabolic, a hyperbolic, as well as an elliptical equation. Okay, so one thing before I go with, I call this PVP, but I need to go a little bit in depth. So basically, this is the thing. Wherever I have some kind of time dependence, I need to have initial conditions. Okay, so let's write this down. I need to have some type of an initial condition. And this is only applicable for the first two equations, which are the 1D heat equation and 1D wave equation. So 2D Laplace equation doesn't have any time dependence in it, so I don't really need an initial condition. And typically, you don't have to, but it's much more convenient to give initial condition at t is equal to 0. Okay, but you don't have to. And I'll give you an example. Let's pick up the heat equation. I can say that, hey, U, which is the temperature, x comma t is my solution. Okay, I can say that U, x comma 0, you can see t is equal to 0, is, I don't know, some kind of a distribution, temperature distribution, f of x. So I can use this, and I can go ahead and find this solution. Once I find my solution, I should ensure that this satisfies this equation. Okay? Or I can give another example from wave equation. Let's write wave equation. And in the wave equation, I can specify to you that my u, which is the displacement in this particular case, x comma 0, again t is equal to 0, is f of x. Very similar, right? So this time I can prescribe you the displacement, or I can actually go ahead and give you or prescribe you the velocity as well, because I know that it's del u del t, and I have t is equal to 0, and I will have, I don't know, g of x, another function like that. Okay, so these are all possible initial conditions, so we will be exposed to that. Okay, and other thing is I also will have boundary conditions. Okay, boundary conditions. So this prescribes as a function of location, right? Let's also pick up the wave equation while we are there. Actually, let me go ahead and draw this for you. So like this, and it's called plucked string. So I can just, it doesn't have to be right in the middle. Anywhere, I can simply just hold this and pull this up, right? This was the equilibrium position, and I just pulled it up here, okay? But you can see what happens to the boundary conditions. Let's say that this is x is equal to 0. Let's say this is x is equal to L. So I will have u 0 comma t is equal to 0. U now L comma t is equal to 0. So you can see that I'm specifying this where it's not a function of time anymore. It now is a function of the location. It's also important to note that there are 3 types of boundary conditions that I can specify. These 3 are, let's write this. The first one is called the, simply I can go ahead and, let's say this is the wave equation, so I can give you the displacement, okay? So this is called the Dirichlet condition. Or I can have del u del n, where n is normal to the, well, we're talking about boundary, so it's going to be boundary. Okay, so this n is normal to the boundary, and this has a name as well. This is called the Newman condition. Okay, and the third one is kind of like combination of 1 plus 2. Okay, so there's nothing new that we're introducing in here, so I can have del u del n plus some kind of a constant times u, and this is a constant. And this is called Robin condition. Okay, so why don't I apply this to a heat equation? Okay, let's be specific. Let's start with the first one. Well, I already gave this to you, but it's like this. So basically, I have myself a rod, and in this rod, what I'm saying is this is x is equal to 0, this is x is equal to L. What I'm saying is initial condition at this end is equal to T0. Okay, that is fairly reasonable, you know, in real life applications we come across this often. The second one is more interesting. Del u del n at x is equal to L can be 0, right? So I'm not going to go too much in depth because this typically is covered in the heat conduction, and we have a course on that, right? Advanced heat conduction. You know, you'll go much more deep than what I'm doing now, but basically this means that we are looking at the heat flux at this end of this rod, and as the heat flux is equal to 0, that means that this is insulated. Okay, so I'm insulating this end of it, all right? And I can combine 1 and 2, and I'll get something called this. Let me write it. So I can have del u del x at x is equal to L at the same location. I'll have myself minus h. H is the convection heat coefficient, u L t minus u of ambient temperature. Okay, So what this is this means that I have a convection. So this is exposed to, let's say, air over here, and there's some convection happening at the end of the rod, and this heat is transferred to the air or water. And medium, I'm keeping it at a constant ambient temperature that I have over here. You may ask, why do I have a negative? The assumption is that this is higher temperature than the ambient. It's just an assumption by convenience. Okay, so far I did the initial value. Now I did the boundary condition. So now I will look at the boundary value problem. Okay, so it will incorporate both of the initial condition and boundary conditions. Okay, as needed, obviously. So let's write this here. Boundary value problem BVP. Okay, as I mentioned, it can have initial conditions. It doesn't have to be, right? We discussed that. The Laplace equation doesn't need initial conditions. Or it will include the boundary condition. All three will have boundary condition, okay, depending on the case. So I'll give you an example from the wave equation, then I'll also give you an example from the Laplace equation because I didn't really go there yet. If I rewrite the equation, del square u del x square will be equal to del square u del t square, right? And I'm subjecting this to, let's give you, an example. U, and I'll ask you what it means, is equal to 0. U, L comma t is equal to 0, where t is larger than 0 without saying, right? So these are the boundary conditions, right? I'm not specifying the time. Time is variable over here, but I'm prescribing the location. So that's why this is called the boundary conditions, all right? So these are boundary conditions. And I'm saying that just like up here, I don't want to redraw the same thing, but right here, it's the same thing, right? I already written this. So this is fixed, this is fixed, all right? Okay, that's the, how about the initial conditions? Okay, I can give you initial conditions like this. How many initial conditions do I need to give? 2, right? Because it's a second order. So I'll give you, for instance, u, x comma 0. You see what I did now? I fixed the time. And now I'll have f of x. And I need to give one more. Let's say that del u del x at t is equal to 0 is equal to g of x. I also talked about this as well. Okay? So let me go up here instead of redrawing it. But what I'm saying is, at the initial time, it's called the plug string for a reason. I pull this, and this is basically the f of x. Okay, this function I'm giving you, this is f of x, right? Because it's the displacement basically. But also the g of x is the velocity. So at time is equal to 0, I'm pulling over here, but who knows? Maybe I'm just pulling it this way up, or I'm pushing it down when I'm not just simply letting it go. Okay, so that will be my another initial condition. All right, let's go out and analyze the Laplace equation. I didn't really talk about that. Del square u del x square plus del square u del y square is equal to 0, like 2D Laplace, not 3D. So let's say that this is my boundary. So actually, why don't I go ahead and draw this? So I have this, let's say that this point is 0, 0. This point will be in the x, so I'm saying that this is x, this is y, right? A comma 0, this will be a comma b, 0 comma b. So now I will solve this temperature distribution in this particular plate. But I don't see any time, right? Important. So everything that I'm going to give you will be the boundary conditions. I'll give you an example. Let's start with the x, then I'll go to the y. In the x, I can do this. Del u, del x. At x is equal to 0 is 0. We discussed this in the heat. This means that this is insulated, right? The heat flux is 0. Okay, how about, let's give this del u, del x, and x is equal to a, the other end of the spectrum. I can say this is also insulated, so insulated these two ends for this particular example, right? That's all I need for the x direction, because you can see it's a second order. I have a second order, so I have to have two boundary conditions for y, and I can prescribe them this way. U, x comma 0, did you see what I did? I now fix the y, right? I say that, hey, it's at y is equal to 0, so I'm talking about this particular surface. Okay, this is given as 0. So, okay, I know the temperature right over here, T is equal to 0, temperature is equal to 0 right there. And I'll give you another one. u x comma b, now I'm looking at this top over here, this can be f of x. Actually, we're going to solve this. All right, so this will be f of x as an example. So I have insulated here, I have insulated in here, I have t0 here, and I have f of x up there. So this kind of summarizes what I need to talk about. Now you know the classical PDEs. The first thing I'm going to do is I'm going to focus on the heat equation and go and solve it. All right, it'll be fun, you'll see. Thank you for watching this. Take care.